and they don't have to be in like MLA format or anything like that. You can just like look at the website. That's it. So that just wants to see that like you have news sources and can make stuff up.
Okay, you guys are doing okay? Is it warmer now outside or still cold? Too much warm?
So, you know, I got an email saying we get an unlimited time frame.
Yeah. Only unlimited time, not twice.
Yeah, like time.
Yeah.
I can't access it. I wanted to, there's the one that had...
You can't open the quiz?
No, it just tells me that my time has run out.
Did you check it again?
I've checked it like 5 times since Monday.
Did you log out completely, turn off your browser, and then sign in again?
When was the last time I checked it? Because when I first went, I could do
Like
it
last
yesterday.
Why don't you come to my office afterwards? Someone else also had a problem like that, and they fixed it later because they signed out and signed in again.
That's right.
It'll be fine.
Yes, if you don't completely sign out, sometimes it keeps the previous work. So just completely sign out. Any questions from anything that I did last time? Hey, wait a minute. I am doomed. I forgot to bring my class notes, so I gotta bring them.
Don't come back. Third grade. I guess I could do that. So it's like middle school. I'm just imagine something.
Okay, so I'm going to start out with an example. This example will be used later as well. So, suppose that you are looking at the limit as x going to 0, absolute value of x divided by x. And so the question is, what's the limit? In this case, if you plug in 0 for x, you see that you get 0 over 0. So the function is undefined. But again, just because the function is undefined doesn't mean the limit doesn't exist, right? So how do we come up with the limit, or how do we justify that the limit doesn't exist? So whenever you have absolute value functions, so the absolute value functions with absolute values are tedious to work with. So usually you want to get rid of them. So how would I get rid of the absolute value sign? Well, x goes to 0 from either side. So x could be positive or negative. So we are going to compute this quantity according as x is positive or negative. So notice that when x is positive, right? When x is positive, what can you say about this ratio? I already said this ratio is undefined at 0. So when x is positive, what can you say? Well, when x is positive, what is absolute value of x? If x is already positive, it is just x, right? And then it becomes what? 1. I think it's hard to see maybe I should turn on one of the lights. Okay, so then what happens when x is negative? When x is negative, what is absolute value of x? Negative x. Because if x is already negative, right, how do you make it positive? You multiply by another negative 1, right? So this would be this, which would be negative 1. So this is when x is negative. So what are we seeing here? We are seeing here, what we are seeing here is that when x is positive, the function is equal to 1 always. When x is negative, the function is always negative 1. So what will be the graph? How will the graph look like? So let's say this is the x-axis, my y-axis, and let's say this is the height at 1. You know what? And let's say this is the height at negative 1. Okay, so this would be positive 1, this would be negative 1. So what's the graph of this function? What do I have to erase? When x is positive, the value of the function is given by this, and when x is negative, the value of the function is given by negative 1. And notice that I am going to have a hole right here and here because the function is undefined at 0, right? So the graph of this function is exactly given by that. So does the limit exist at 0? So what we see here is that this limit does not exist. So however, what can we say about the right hand and left hand limit? What we see here is that the limit as x going to 0 from the right of absolute value of x over x is 1, and the limit as x going to 0 from the left, absolute value of x over x is equal to negative 1. Now in your homework, you'll see that there are some problems where you're being asked to find limits, and the functions have absolute values in them. How would you do those problems? Well, the first thing you have to do is get rid of the absolute value sign according as the values of x. So maybe instead of absolute value of x, if you have absolute value of x minus 3, then you are going to write this without the absolute value according as what? According as x bigger than 3 or less than 3, because x bigger than 3 will mean it's positive, x less than 3 would mean it's negative. Am I making sense? So you're going to break up the definition of the function at 3. Okay, so keep that in mind when you do your homework problems. Next, maybe I didn't write it down in this class, I did in the other class. The limit as x going to a from the right of f of x is equal to the limit as x going to a from the left of f of x if and only if the limit as x going to a of f of x is equal to L. I need to say is equal to L right here as well. So what I'm saying is that if the right hand limit and the left hand limit, they are both equal to L, then the both sided limit is also L, and vice versa. Okay, so I guess you already realize that. So now here, so far, I have shown you examples by using graphs and sort of given you examples of limits based on, by looking at graphs and stuff like that. What I want to do now is to show you how to so now I want to develop limit rules to come up with limits of the basic functions, okay, like polynomials, rationals, and other functions. So how can we come up with the limits of how do we compute limits of functions? And to do that, we are going to come up with a couple of limit rules and use them to compute limits. Okay. The first thing is the following theorem. Again, at this point, if you already have taken calculus, please just forget about any of that. Otherwise, it's hard to see how these are developed. So let's let because if you already know how to compute the limit of a polynomial, then you're probably just going to sleep until I get there. So let's let C be a constant. And let f of x be the function whose value at x is always c. So it's the constant function. So then what's the limit as x goes to a of the constant function c? Well, the limit should be what? C itself, right? For any real number a. So for any real number a, that's the case. Well, the reason is pretty clear, but let me again sketch the graph of this guy. So if c is positive, the graph would be like what? It will be a horizontal line like this, right? So this is the line y equals to c. So if c is positive, the graph will look like this. And so if I take any real number a, what's the limit? What's the limit of the function as x approaches a? As x approaches a, the value of the function is c. It goes to c, while in fact the value is always c. So there is no surprise. So that's one rule that we're going to use. The second rule we are going to use is that the limit as x going to a, of the function x, I'm saying what's the limit of x as x goes to a, right? What's the limit of x as x goes to a? Well, as x goes to a, x goes to a, right? So the limit should be a for any real number a. In this case, we also know the graph. Notice that the graph in this case would be a straight line, right? And this is the line y equals to x. So if I pick a number a, then what's the height of the graph at a? What's the height of the graph at a? A as well, right? And now we are saying that what happens? What's the limit as x approaches a, right? Well, the question is, can I make the value of the function as close to a as I desire by picking x sufficiently close to a? The answer is obviously yes. So the limit is the limit of x as x goes to a is a. Okay. Now the algebraic rules. So now the algebraic rules of limits. So some limit laws. I should say the algebraic limit laws, but so we are going to suppose here, the limit as x going to a of f of x, and the limit as x going to a of g of x, they both exist. Okay? These limits are some numbers. So rule number 1. I didn't give you this last time, did I? No. Okay, rule number 1, the limit as x going to a of f of x plus or minus g of x. So if I know the limit of f, if I know the limit of g, what's the limit of the sum or difference? Well, it's just the sum of the limits. So limit x going to a of f of x plus or minus the limit as x going to a of g of x. Okay? So what this is saying is that if you have a sum, right, you can take the limit of each term. So you can take the limit term by term. Okay? One term at a time. You could do that as long as the limit of each term exists, right? This is saying you can take the limit of a sum by taking the limit of by taking limit term by term, as long as the limit of each term exists. Okay. Notice that there are situations where let me give you an example here very quickly. So notice that here I have if I look at the limit, let's say x going to 0 of 1 over x minus 1 over x. Okay. What's going to happen is that the limit of each term, in fact, in this example, doesn't exist. So if you look at the function 1 over x, as x gets closer and closer to 0, 1 over x does not approach a number. Am I making sense? And so each term in the sum doesn't have a limit. However, notice, so I cannot take the limit of here. Am I allowed to take the limit term by term? No, I cannot take the limit. I can. I mean, if I do, then what would be my answer? I would say that the limit of this guy doesn't exist, this guy doesn't exist, so the limit doesn't exist, right? Mm-hmm. But this rule you cannot apply if the limit of each term does not exist, right? This rule doesn't apply if the limit of each term does not exist. So when you have a situation like this, obviously, what's the limit though? Yeah, because it's really 0 in these guys, right? It's just a 0 function, right? So the limit of this guy is in fact 0. Notice that the limit of the terms don't exist, but the limit of the sum exists, right? So you have to be careful. When you apply that, the limit of each term must exist. If the limit of each term does not exist, this law doesn't apply. Okay, so limit law 2. What's the limit as x goes to a of the product of f and g? So if you're taking the limit of a product, that's the same as the product of the limits of the factors. So you take the limit of f times the limit of g. So basically, if you have a product of functions, you are allowed to take the limit one factor at a time and then multiply them, right? The limit of a product is the same as the product of the limits of the factors. Okay. Again, in this case, for example, notice that if I take the limit as x goes to 0 of 1 over x times x, right? So here I have two factors, right? And if I take the limit term by term, what's going to happen? The limit of 1 over x times the limit of x. So it'll be limit of 1 over x doesn't exist as a number. Limit of x is 0, right? So what would be the limit of the product? So my point is you cannot apply the law, number 2, in this case, because the limit of 1 over x doesn't exist. So the limit of each term has to exist before you apply the law. However, notice that even though the limit of each term doesn't exist, one of the terms doesn't exist, the limit of the product exists. It is 1 because I really have 1 in these guys there, right? Okay. The key is just because the limit of a factor doesn't exist doesn't mean that the limit of the product would not exist. Okay. All right. 3. What would be the limit as x going to a of f of x divided by g of x? Well, this limit would be, ratio of the limit. So you take the limit of the numerator as x goes to a, and you take the limit of the denominator. And what condition do I need here? Notice that this wouldn't work if the limit of the denominator is 0. So I have to put a condition here that the limit of the denominator must not be 0. Otherwise, you can't apply this equation. Is everybody okay with that? Okay, 4. What would be? I think. All right, so I have to write it here, but I wanted to write it in number 2. For any constant c, the limit as x goes to a of c times f of x. So if you have a constant factor in your function, that can be factored out of the limit. So it would be c times the limit of f. I'll demonstrate this in a bit in an example. And then 5. The limit as x goes to a of f of x to the n is the same as, so you have the nth power of a function, let's say n is 50 or something, then when you take the limit of that, what you have to do is take the limit inside the exponent, take the limit of the base function, that is, so you take the limit of f of x, and then you raise the limit to n. And this here, n is a positive integer. Remember, this symbol means the collection of positive integers. One more. How about the exponent? How about taking roots of functions? So if I am taking the limit as x goes to a of f of x to the exponent 1 over n, so this is the root of this, then what would be the limit? The limit would be, you take the limit of the base function, and you take the nth root of that. Again, n is assumed to be here. Okay. However, there is a little bit of problem with number 6, which is if n is even, right, like half, that if you're taking square root, what if the limit of f is negative, right? If the limit of f is negative, then you cannot take even root of that, right? So we have to say something about that then. When n is even, we require the limit of f to be what? Yeah, we want that to be non-negative. Very good. Okay, so these are the limit rules, and what I'm going to show you now is that these limit rules will allow us to compute the limit of a polynomial function very, very easily. So let's see how. So here is an example. Let's say you are taking the limit as x goes to 5 of 2x squared minus 3x plus 4. Okay, so let's apply the laws one by one. What's the first law? It says that if you have a sum, you can take the limit term by term, right? So take the limit one term at a time. So I take the limit of the first term minus the limit of the second term plus the limit of the third term. Okay, so that's the first law. And then law number 4 that I wrote, it says that if I have a constant factor, I can take it outside of the limit. So I can write 2 times the limit as x goes to 5 of the function x minus 3 times the limit as x goes to 5 of x plus the limit. I'm just going to keep it the way it is. X goes to 5 of 4. Now remember, I have the second theorem says the limit of x as x goes to a is a, right? So what's the limit of x as x goes to 5? That's 5 minus 3 times 5, and the limit of a constant is the same constant, right? 4. So that's the limit. So if I apply all these rules, I know what you're going to say in a bit. If I apply all these rules, I get this. Now look at what's the net work we have done here. As we applied the laws, what is the net work at the end? What's the net work that I have done? Oh yeah. Were you going to say that? I thought you were going to say something else. You're going to answer my last question, I thought. Okay, so this should be this, and I have to erase everything else. Thank you for pointing that out. So here what I need to write is 2 times the limit as x goes to 5 of x. Remember, this is the limit law number what? So this is where we applied 1, this is where we applied 4, this is where we applied 5, minus 3 times the limit of x as x goes to 5 plus the limit as x goes to 5 of 4. And so what am I getting? I'm getting 2 times 5 squared minus 3 times 5 plus 4. Can somebody tell me what is that? How much is that? 39. Okay, now my question again, what's the network that we have done? what is the net work that we have done? We started out with the limit of 2x squared minus 3x plus 4. We applied this loss, and then we came up with that numerical answer right here. What's the net work? The net work that we have done is we replaced x by 5, right? If you look at my final answer here, and then we tried to compute this limit, all I really did is plugged in 5, right? So this loss, if we apply, the net work that we are actually doing is plugging in that 5. And this is in fact true for any polynomial. So if you are computing the limit of a polynomial at a number a, all you have to do is plug in that a. Okay? So let me now write that down. Theorem. If p of x is a polynomial function, then the limit as x goes to a of p of x is equal to p of a. All I have to do is plug in a for x and compute the value of the function. Is everybody okay with that? An example, again, if I take the limit as x goes to negative 2 of 5 minus 3x, what is that equal to? Well, all I have to do is, it's a polynomial. By the theorem, I know that all I have to do is plug in a negative 2 for x. If I do that, I get what? 11, right? Okay, now, so that's for polynomial functions. How about rational functions? So here's an example. Let's say you now want to take the limit of a rational function as x goes to negative 2. Let's say what I have is x cubed plus 2x squared minus 1 divided by 5 minus 3x. I have a ratio of functions, right? Rule number 3, right? Rule number 3 says, how do I compute the limit of f divided by g, right? How do I find it? Well, I just take the limit of the numerator divided by the limit of the denominator, as long as what? As long as the limit of the denominator is not 0. Notice that, what's the limit of the denominator here? We already took it. I know that it's not 0, right? And since it's a polynomial, I can find the limit by just plugging in the limiting point. So here I take the limit so I have to take the limit as x goes to negative 2 of x cubed plus 2x squared minus 1, and that is equal to what? Polynomial, so I just plug in, right? So it will be negative 2 cubed plus 2 times negative 2 squared minus 1 divided by 5 minus 3 times negative 2, and which is what? Is that 1 over 11 or negative 1 over 11? So I could do that because the denominator doesn't vanish, right? The limit of the denominator is not 0. So if you think about it again, what's the net work I did? Net work I did, if you look at my fraction here and the fraction here, all we did is replaced x by negative 2 again. So what can we say then? Well, if I have a rational function, if the denominator doesn't vanish at the limiting point, then the limit of the rational function can be found by just replacing x by the limiting point. So So now we could say this is for any rational function where the denominator doesn't vanish at the limiting point. So this is if R of x equals to P of x divided by Q of x is a rational function and a is a real number which is in the domain of R, then A is in the domain of R, it means what? For a rational function, A is in the domain as long as the denominator is not 0 at A, right? So then we could say that the limit as x goes to A of this rational function is simply plug in A for x. Is everybody okay with that? So now you know how to find the limit of a polynomial. How do you find the limit of a rational as long as the limiting point is in the domain? What if the limiting point is not in the domain? What do you do then for a rational function? That's what we want to look at now. So here's an example. The examples that I'm doing here, you should try to remember for what type of functions, what trick I am applying. Okay, if you remember that in your homework, you'll see that if you remember that, you'll be able to do them easily. So here's a problem where I have a rational function x squared minus 9 over x minus 3. And I am taking the limit as x goes to 3. So notice in this case what's going on. What's the limit of the numerator as x goes to 3? What's that? 0. And what's the limit of the denominator as x goes to 3? 0 divided by 0. Now the function is undefined at 0, that's clear. But remember again, the function is undefined at 0 doesn't mean the limit of the ratio doesn't exist. Am I making sense? The function is undefined at a point doesn't mean the limit doesn't exist there. Okay? Every time I taught this course, every time I had the first exam, every time I put this problem, there is somebody who's going to say that the limit of this function doesn't exist because it is 0 over 0. Okay? Please be warned, that's not true. Okay? Now, what is true is the following. Whenever you have a situation, if you have a rational function, and then you plug in the limiting point, you get 0 over 0. So what does it mean? It means that the polynomials vanish at 3, right? So the numerator vanishes at 3. Remember what I said about polynomials? If a polynomial vanishes at 3, then x minus 3 would be a factor of that polynomial, right? So because of this, it tells you that you can factor out the polynomial. And one of the factors would be x minus 3, which is a good thing because then you can cancel out the x minus 3 in the denominator. Am I making sense? So whenever you have a rational function, you have 0 over 0 when you plug in the limiting point. The trick is factor out. So we are going to do just that. Factor this out. And if I factor this out, the good thing is x minus 3 cancels out. I get x plus 3. So what does it tell me when I cancel out the x minus 3? It means that the fraction, the value of the fraction is the same as the value of x plus 3, except at 3, right? So these are the same functions except at 3. But I don't care what happens at 3. I care when x is close to 3. So the limit of this guy is the same as the limit of x plus 3, which is what? Now I can plug in because it's a polynomial, right? I can plug in and that's just 6. Is everybody okay with that? Now let's do a similar example. What if I take the limit as x goes to, let's say, x minus 1, x goes to 1, so x minus 1 over x squared plus x minus 2. Once again, let's notice that when I plug in 1, the numerator vanishes. And how about the denominator? Vanishes as well. So again, I have a rational function. The numerator, the denominator, they both vanish at the limiting point. What's the trick? Factor out. So, I get x minus 1 over, if I factor out, what do I get? X minus 1, I better get that, otherwise factoring out doesn't help. And then, what else? X plus 2. Now, you know that I am going to get x minus 1, right? Because the denominator vanishes at 1. That tells me x minus 1 is a factor. Okay? And I am guaranteed that that's going to happen. So now if I cancel them, I get a 1 in the numerator. And then now I have a rational function. Now it's a rational function where the denominator doesn't vanish at 1 anymore. So I can find the limit by just plugging in, right? Which would be 1/3. Is everybody okay with that? You're going to have similar problems in your homework. If you just remember the trick, 0 over 0, factor it out. Again, I tell you one thing, that every time I taught this, it happened that somebody will say, the fraction, when I plug in, I get 0 divided by 0, therefore the limit is undefined. The function is undefined, but the limit is not undefined. Is that okay? The only reason you're going to miss this question in the exam is what? Is that you don't do your homework, right? So, and this is going to be it's coming soon in something, not in theaters, but it's coming soon. It's coming soon, whenever your next exam is. Okay. So pay attention to this problem. Okay, so here's another example. Let's take the limit as h goes to 0. 3 plus h squared minus 9 divided by 3h. So let's say I have this limit problem. If I plug in the value of h, what do I get? Do I get 0 again? Do I get 0 in the denominator? Is this a rational function? So instead of h, replace h by x, right? And do you think I have a polynomial in the numerator? Yeah, you have 3 plus h, right, squared. So if you use FOIL, multiply 3 plus h, you only end up with powers of h, right? So it's a polynomial, right? So like I said, if you have a polynomial over a polynomial that is a rational, 0 over 0, what do? Factor out. Well, you can factor it out, but I'm going to do something else here. The numerator, notice that sometimes if you don't know what to do the obvious algebra. What's the obvious algebra here? You have a square, FOIL it. Okay? So the limit as h goes to 0. If you FOIL 3 plus h squared, what is it? 3 squared is 9 plus 6h plus h squared. Very good. This is 9. Notice that 9's cancel out, and then I have h goes to 0. Now, all I have is this is left, right? Can I factor out h and write it as what? 6 plus h divided by 3h. And now I can say cancel out the h's, right? And now when I plug in h equals to 0, what do I get? I get 2 as the limit. Is that okay? So sometimes you just have to do the obvious algebra and see what happens. Here's another example where you do get 0 over 0, but you don't have a rational function. Okay, you have some root functions there. So here's the example, and you're going to thank me that I reviewed algebra at this moment. So as x goes to, let's not use x. I think I have overused x. Okay, t goes to 0. Let's say what I have is the following. Not there. All right, here. Root of t squared plus 9 minus 3 divided by t squared. Okay. What happens when I plug in 0 for t? The denominator I get 0, right? In the numerator, do I get 0 as well? Because I get root of 9, which is 3 minus 3. The problem is I don't have a rational function, so I cannot say factor out. Okay? So what should I do here? I cannot factor out, so what should I do? You realize that computing this type of limits means that I need to get rid of the factor in the denominator, which is giving me 0. Right? In all these examples, you you were successful because you got rid of the factor giving you 0 in the denominator. Here, what's the problem in your review algebra homework that you did, where you saw something like this function? In your review algebra exam or homework, didn't you see this type of functions, and what did you do with them? What was the question involving root functions in the review algebra? Rationalize the numerator, right? Rationalize the numerator. So once again, when you see something like this, this is a cliche in calculus. In most of the problems, whenever you see root functions and you're computing limits, root functions, if you can't think of anything else, rationalize and see what happens. So in this case, you are going to rationalize the numerator, t squared plus 9 minus 3 divided by t squared, and then what you're going to do is multiply and divide by the conjugate of the numerator. So what is that? It's going to be this plus 3 divided by this plus 3. And I am going to do the harder part, which is you multiply the denominators, and I'll let you do the multiplication of the numerator. So in the denominator, when I multiply, what I get is this. That's a lot of work, so I leave it there. Sometimes in the exams I see that people multiply out the denominators, okay? And once you do that, you will have no clue what to do, okay? Remember, the deal here is that you want to get rid of t squared in the denominator, because that's what giving you 0 in the denominator. Your goal should be to try to get rid of t squared. So at this point, if you multiplied out the denominators, you wouldn't be able to get rid of t squared. Now, what happens when you multiply out the numerators? When you multiply out the numerators, you're going to use FOIL. Okay, what's going to happen, since I don't have time, you're going to get t squared plus 9 minus 9. And that's going to get rid of the 9s. Once you get rid of the 9s, you can also get rid of what? T squared, and we're going to end up with a 1. And at this point, you can plug in 0. If you plug in 0, you're going to get root of 9 plus 3, which would be 1 over 6. Once again, this is one of my favorite problems, okay? So it might be coming soon as well. Okay. So.
I don't know if Ada can get this.